Josh, can you turn on the lights, please?
So, quantum physics suggests that something doesn't exist if you don't recognize it's there.
Absolutely.
It's consciousness.
That's correct. That's one of the more out there theories. The fact that the observer has to be conscious is debatable, but
Yeah, that really breaks science.
that really would. Okay, everybody have a piece of paper. So we gotta discuss three classical postulates that describe how black body spectrum work. Okay, and these were semi-correct. Okay, so from classical mechanics, that's where we're going to start from. When we were doing harmonics back when we were just talking about waves, if we had a standing wave along a simple spring, we'd keep creating more and more nodes in that standing wave just by increasing the frequency. Well, it turns out that a black body molecule doesn't respond quite the same way. It can only have a certain finite number of harmonic vibrations. Okay, so we have the vibrations and its fundamental frequency, then we've got the extra harmonics over top of it, just like we've talked about before. And molecules we vibrate, but those harmonics don't exist indefinitely. Okay, they're based on frequency squared. That's right. The second postulate that classical physics said is that, and this one is not correct. This one says that the energy of all the different modes, all those different harmonics, are just based on the temperature of the overall black body. Do you guys think that K is E equals KT? Yeah, good.
Let's try this again. 6.67 times 10.
Oh no, not the Boltzmann dash. You're thinking Avogadro. Yeah, not Boltzmann. No, just Boltzmann. This is the 5.67 times 10 to the negative 8.
Right.
And the third and most incorrect postulate from classical physics is, unfortunately the scroller doesn't work. I have to keep coming back to my computer. Okay, is everybody done with postulate 1? Okay. what this states is that the probability of a molecule vibrating at a super fast harmonic or a super high harmonic is equal to its probability of vibrating at its fundamental frequency. Which is kind of strange. You'd think that, and what is true is that the higher the vibration, the more energy it takes. And that would mean there's less probability of that molecule vibrating at that higher state. And that's what we're going to find out is true. But in the late 1800s, they thought that for all of the molecular vibrations of a black body that's producing the temperature, or producing the range of frequencies, they said that all the probabilities are identical, whether a molecule is vibrating at a really high frequency or really its fundamental frequency. Okay, so this is the one that ends up being the downfall to the classical interpretation of the black body spectrum.
Okay, so this is false then. So the probability is not equal because of the change in temperature.
That's right.
Okay.
That's exactly right. Classical physics predicts that the energy of a black body is proportional to the wavelength of that black body to the power of -4, which results in something called the ultraviolet catastrophe. Okay, and it's like literally the part of physics where classical physics is proven it's not enough. We need more. Okay, so I'm going to go to the next page here.
It sounds pretty dramatic.
It is. I mean, it's a catastrophe because everything that scientists thought about the way thermal physics works is now obsolete. Talking centuries of theory. Okay, we're just gonna need a set of axes on your notes. No, in the macroscopic world, we're good. We're okay. And the equation, like the Boltzmann equation, where the power is defined by that those equations are still valid. It's just
we're looking at specifically at the molecules of black holes.
That's right. Yeah. Sorry, what's that?
Does it need the transfer of energy to the microscopic state?
Yeah.
So it's still microscopic.
True. What's your question?
You're saying that you're supposed to, it shouldn't work in the microscopic world.
No, honestly, classical physics predicted that any black body would have enough energy, would have an infinite amount of energy. So anything that had any temperature above 0 Kelvin would melt your face off if you looked at it. So in order to resolve this, obviously that wasn't experimental, but in order to resolve it, we needed what we're going to see is the Planck constant. Okay. Now the power we didn't need, for the power of a black body curve, we didn't need that, but we did need that for to model it. Sorry, escape. So we've got energy on the y-axis. Okay, and we've got frequency on the x-axis.